Picture this for a moment. Every single atom in your body, every star in the night sky, everything you've ever touched or seen has a hidden twin. Not just any twin, an exact opposite version that could wipe it out of existence in an instant. This isn't science fiction. It's real, it's called antimatter, and it's one of the universe's greatest unsolved mysteries. Right now, as we speak, physicists are smashing particles together at nearly the speed of light to create these bizarre mirror particles. But here's the twist. When the universe began, there should have been just as much antimatter as regular matter. They should have cancelled each other out, leaving nothing behind. Yet somehow, here we are in a world made entirely of matter. So where did all the antimatter go, that tiny imbalance? Just one extra matter particle for every billion antimatter particles is the reason you exist. Without it, there would be no planets, no stars, no you, and no one knows exactly why it happened. Over the next few minutes, we're going to explore the wild theories scientists are testing right now, from cosmic glitches in the laws of physics to invisible particles that might hold the answer. And by the end, you'll see the universe in a whole new way. So let's start at the beginning. What exactly is this ghostly counterpart to everything we know? Now, to understand this cosmic mystery, we need to get familiar with antimatter itself. Think of it like this. If matter is the protagonist of our universe, antimatter is its perfect villain, almost identical but with one crucial difference. Antimatter particles are like mirror images of their matter counterparts with the same mass but opposite electrical charges. Take the electron, for example. Its antimatter twin is called a positron, identical in every way except it carries a positive charge instead of negative. Same goes for protons and their antiparticles, antiprotons, which are negatively charged. Even quarks, the tiny building blocks inside protons and neutrons, have antimatter versions called antiquarks. This bizarre idea wasn't pulled from thin air. Back in 1928, a brilliant physicist named Paul Dirac was playing around with equations describing how electrons behave. His math kept suggesting something strange. For every possible electron solution, there should be an opposite version, almost like a shadow particle. At first, he thought it was just a quirk in the calculations, but 2 years later, scientists actually detected positrons in cosmic rays, proof that antimatter was real. Fast forward to today, and we're creating antimatter right here on Earth in places like CERN. Using massive particle accelerators, physicists slam protons together at nearly the speed of light. These high-energy collisions can spontaneously produce matter-antimatter pairs, just like the early universe did. But here's the catch: making antimatter is incredibly hard, and storing it is even harder. Since it annihilates instantly upon contact with regular matter, labs use powerful magnetic fields to trap antihydrogen atoms, antiproton and positron combos in special vacuum containers. And that brings us to the most explosive part. When matter and antimatter meet, they don't just fizzle out, they unleash pure energy. A single gram of antimatter colliding with matter releases the equivalent of a 20-kiloton nuclear bomb. That's why in science fiction, antimatter is often the ultimate power source or doomsday weapon. But in reality, producing even a speck takes monstrous amounts of energy. CERN makes about 1/1000th of a gram per year, barely enough to power a light bulb for a few seconds. So why go through all this trouble? Because studying antimatter might hold the key to why our universe is made of matter at all. Every time we create these particles in labs, we're replaying the universe's earliest moments on a tiny scale. And somewhere in that asymmetry, some tiny deviation in how matter and antimatter behave, could lie the answer to one of physics' biggest questions. Next up, we'll dive into that very puzzle. Why didn't the Big Bang's perfect symmetry between matter and antimatter last? The clues might be hiding in cosmic glitches called CP violations. Let's peel back the layers of this cosmic mystery. If the Big Bang truly created matter and antimatter in equal amounts, they should have completely annihilated each other, leaving behind nothing but pure energy. Yet here we are, in a universe brimming with galaxies, stars, and planets all made of matter. So where did all the antimatter go? This glaring asymmetry is one of physics' most baffling puzzles, and it's called the matter-antimatter symmetry problem. To grasp why this is so strange, imagine a perfectly balanced seesaw. On one side you have matter, on the other antimatter. The Big Bang should have placed equal weight on both ends. But instead, the seesaw tipped violently in matter's favor. For every billion antimatter particles created in the early universe, roughly 1,000,000,001 matter particles survived annihilation. That tiny 1 part in a billion imbalance is the reason anything exists at all. So what could have broken this perfect symmetry? Enter baryogenesis, the process that might explain how matter came to dominate. The term comes from baryons, particles like protons and neutrons that make up ordinary matter, and genesis, meaning creation. Physicists believe that in the universe's first fractions of a second, some unknown mechanism skewed the scales, allowing matter to edge out antimatter. The leading theories point to 3 key ingredients needed for baryogenesis, first proposed by physicist Andrei Sakharov. First, there had to be a violation of something called CP symmetry, a rule that says the laws of physics should treat matter and antimatter identically, even if their charges and spatial orientations are flipped. But in 1964, scientists discovered that certain particles called kaons violate this rule, behaving slightly differently from their antimatter counterparts. This tiny crack in the symmetry could be the first clue. Second, the early universe needed conditions where baryon number wasn't strictly conserved. That means processes could create more baryons matter than antibaryons antimatter. And third, these processes had to occur out of thermal equilibrium. Think of it as the universe being too hot and dense for annihilation to erase the imbalance as fast as it formed. Here's where it gets wild. If these conditions were met, the imbalance might have arisen from particle decays. Hypothetical heavy particles predicted by theories like grand unification could have decayed slightly more often into matter than antimatter. Over time, that small bias snowballed into the matter-dominated cosmos we see today, but the puzzle is far from solved. While CP violation has been observed, its effect is too weak to explain the universe's current matter surplus. That's why scientists are hunting for even stronger violations in particles like neutrinos or undiscovered supersymmetric particles. So next time you look up at the night sky, remember, the stars you see are the survivors of an ancient cosmic battle, and the answer to why they exist might lie in the tiniest flaws in nature's perfect symmetry. Up next, we'll zoom in on one of those flaws, CP violation, and how a quirky experiment with kaons in the 1960s cracked open the door to solving this mystery. Shifting our focus to one of the most critical clues in this cosmic puzzle, let's examine charge parity violation, or CP violation for short. This phenomenon is essentially nature's way of playing favorites between matter and antimatter, and it might hold the key to understanding why our universe isn't just a sea of empty space. To picture CP symmetry, imagine flipping a particle's charge and its spatial orientation like a mirror image. In a perfectly symmetrical universe, antimatter particles should behave exactly like their matter counterparts when you perform this flip. But in reality, they don't, and that's where things get interesting. The first crack in this symmetry appeared in 1964, thanks to an ingenious experiment with particles called kaons. These unstable particles have an antimatter version known as antikaons, and under normal circumstances, they should decay at the same rate. But physicists James Cronin and Val Fitch noticed something strange. When they observed neutral kaons decaying, the matter and antimatter versions didn't follow the same rules. The antikaons decayed slightly differently, breaking the expected symmetry. It was like tossing 2 identical coins and getting heads more often from one than the other, a clear sign that something was off. This tiny discrepancy might seem insignificant, but its implications are enormous. For the first time, scientists had concrete evidence that the universe doesn't treat matter and antimatter as perfect mirror images. If CP symmetry were absolute, the Big Bang's equal creation of both would have led to total annihilation. Instead, this slight bias in kaon decays hinted at a mechanism that could have tipped the scales in matter's favor. So how does CP violation translate to the universe's matter dominance? Think of it as a cosmic lottery where matter particles had slightly better odds. In the extreme conditions of the early universe, even a 1% difference in behavior between matter and antimatter could have allowed matter to outlast its counterparts. Over time, the surviving matter particles built everything we see today, from atoms to galaxies. Yet there's a catch. The CP violation observed in kaons is far too weak to account for the overwhelming amount of matter in the cosmos. That's why physicists are now digging deeper, searching for stronger violations in other particles like neutrinos or hypothetical supersymmetric particles. These follow-up experiments could reveal whether CP violation is the smoking gun behind baryogenesis or if there's an even stranger mechanism at play. As we piece together this cosmic detective story, CP violation remains a crucial lead, one that reminds us just how delicately balanced our existence truly is. Up next, we'll explore how these clues fit into Sakharov's grand recipe for creating a matter-dominated universe. Now that we've seen how CP violation could tilt the cosmic scales, let's turn to the bigger picture. The three essential ingredients physicist Andrei Sakharov proposed to explain why matter rules the universe. Think of these as the universe's recipe for creating something from almost nothing. First up is CP violation, the ingredient we just explored. Imagine baking two identical cakes but adding a pinch more sugar to one. That tiny difference changes how they rise. In the same way, CP violation gave matter a slight edge during particle decays in the early universe, allowing it to outlast antimatter. Without this imbalance, everything would have annihilated into pure energy, but CP violation alone isn't enough. Sakharov's second condition is baryon number violation. Baryons are particles like protons and neutrons that make up atoms, and their numbers should be conserved, meaning you can't just create or destroy them under normal circumstances. But in the extreme heat of the Big Bang, baryon number might not have been so strictly enforced. Picture a bank temporarily lifting withdrawal limits during a crisis. If particles could briefly break the rules, matter might have been produced in excess of antimatter. The final piece of the puzzle is non-equilibrium conditions. In a calm, balanced environment, matter and antimatter would annihilate evenly, but the early universe was anything but calm. Rapid expansion and cooling created chaotic, uneven pockets, like shaking a soda bottle before opening it. This turbulence could have frozen in that tiny matter surplus before annihilation could wipe it out. Putting it all together, Sakharov's conditions are like a cosmic lottery. CP violation rigs the game slightly in matter's favor. Baryon number violation allows matter to be created out of thin air, and non-equilibrium conditions lock in the winnings before the universe changes its mind. Yet mysteries remain. While we've observed CP violation, baryon number violation is still theoretical, and non-equilibrium conditions are hard to recreate. That's why scientists are smashing particles in colliders and studying neutrinos, to see if these pieces fit the Sakharov blueprint or if we're missing something even stranger. Up next, we'll see how modern experiments are putting these ideas to the test, hunting for clues in the debris of particle collisions and the shadows of distant galaxies. Shifting our focus from theory to real-world science, let's step inside the colossal laboratories where physicists are putting Sakharov's ideas to the test. At facilities like CERN and Fermilab, scientists aren't just pondering the mysteries of antimatter, they're recreating the conditions of the early universe to hunt for answers. The star of the show is the Large Hadron Collider, the most powerful particle accelerator ever built. Here, protons are hurled at nearly the speed of light, colliding to produce bursts of energy that momentarily mimic the seething chaos of the Big Bang. Among the debris of these collisions, antimatter particles flicker into existence, giving researchers a fleeting glimpse into nature's most elusive symmetry, or lack thereof. But creating antimatter is only half the battle. The real challenge is catching it. Enter experiments like Alpha and Base at CERN, where physicists have pulled off what sounds like science fiction, trapping antihydrogen atoms. Antihydrogen is the antimatter counterpart of hydrogen, made of an antiproton and a positron. To hold these atoms steady, scientists use magnetic fields so precise they're like invisible cages. Why go to such lengths? Because studying trapped antihydrogen lets us compare it to ordinary hydrogen atom for atom. Any tiny difference in their behavior, how they absorb light, how they respond to gravity, could reveal why matter won the cosmic tug-of-war. Recent breakthroughs have already delivered surprises. In 2022, the BASE team measured the magnetic moment of an antiproton with unprecedented precision, finding it identical to a proton's within experimental error. This near-perfect symmetry deepens the mystery if matter and antimatter are so alike. Where did the imbalance come from? Meanwhile, the Alpha-G experiment is testing whether antimatter falls up or down in gravity, a question that could upend Einstein's equivalence principle if antimatter defies expectations. Yet for all these advances, gaps remain. Even the most sophisticated traps can only hold antihydrogen for minutes before it annihilates. And while colliders recreate the energy of the early universe, they can't replicate its vast expansion or cooling. That's why researchers are also turning to cosmic messengers, like neutrinos at Fermilab's Dune experiment, to search for baryon number violation in particle decays. The takeaway: every experiment, whether it's trapping antimatter or smashing protons, is a piece of the puzzle. Some results reinforce Sakharov's framework, while others push us toward new physics beyond the standard model. What's clear is that the answer won't come from a single eureka, a moment, but from patient, relentless testing, one collision at a time. Next, we'll venture beyond the lab to explore where antimatter hides in the wild, from the depths of space to the heart of our own galaxy. Let's take a step outside the lab and into the cosmos, where antimatter isn't just a scientific curiosity. It's a natural phenomenon with its own cosmic playground. Space might be dominated by matter, but antimatter isn't entirely absent. In fact, it pops up in some of the most extreme environments the universe has to offer. First, consider cosmic rays, high-energy particles racing through space at nearly the speed of light. When these cosmic rays slam into molecules in Earth's upper atmosphere, they produce showers of secondary particles, including positrons, the antimatter twins of electrons. These fleeting particles are evidence that antimatter isn't purely a human-made creation. But here's the catch: these positrons are rare, and their production is a side effect of high-energy collisions, not a sign of vast antimatter reservoirs. Then there's the dramatic interplay near black holes. When matter spirals into a black hole's intense gravitational grip, it doesn't go quietly. Friction and magnetic fields heat the infalling material to unimaginable temperatures, creating jets of particles blasted outward at relativistic speeds. In these jets, pairs of matter and antimatter particles, especially positrons and electrons, are born from the sheer energy of the environment. NASA's Fermi Gamma-Ray Space Telescope has detected gamma-ray bursts linked to these annihilation events, painting a vivid picture of antimatter's role in some of the most violent processes in the universe. But perhaps the most intriguing natural antimatter source is the mysterious clouds of positrons floating within our own galaxy. In 2008, astronomers discovered an unexplained excess of positrons near the center of the Milky Way. One leading theory suggests these particles might be streaming from pulsars, rapidly spinning neutron stars that act like cosmic lighthouses, spewing out radiation and particles. Another, more speculative idea ties them to dark matter annihilations, where hypothetical particles collide and produce antimatter as a byproduct. Either way, these antimatter clouds are a tantalizing clue that nature still holds secrets about how antimatter behaves outside our labs. Yet for all these fascinating sources, the overwhelming reality remains antimatter is staggeringly rare compared to matter. If pockets of antimatter existed in large quantities, we'd see the unmistakable signature of annihilation radiation wherever it touched matter. But the universe is eerily quiet on that front. The gamma-ray bursts we do detect are localized and fleeting, not the constant fireworks we'd expect from widespread antimatter. This cosmic imbalance only deepens the mystery. If the Big Bang created matter and antimatter in equal amounts, why didn't these natural processes leave behind more antimatter? Why does it only appear in these tiny, scattered traces rather than in stars, planets, or even entire galaxies made of antimatter? The answer might lie in the subtle asymmetries we're still uncovering both in the lab and in the depths of space. Next, we'll turn our attention to an even more elusive player in this cosmic puzzle, the neutrino, and how its peculiar behavior might hold the key to matter's dominance. Now let's zoom in on one of the universe's most elusive particles, the neutrino. These ghostly particles might seem insignificant, but they could be hiding the answer to why matter rules the cosmos. Unlike the dramatic antimatter signatures near black holes or in cosmic rays, neutrinos operate in the shadows, barely interacting with matter at all. Yet their subtle behavior might hold the key to breaking the symmetry between matter and antimatter. Neutrinos are fascinatingly odd. They're everywhere. Trillions pass through your body every second, but they're so tiny and chargeless that they barely notice the universe exists and vice versa. For decades, scientists thought they were massless, but we now know they have an almost impossibly small mass. This tiny weight turns out to be a big deal because it allows neutrinos to do something extraordinary: oscillate. Imagine a neutrino starting its journey as one flavor, say, an electron neutrino, but by the time it reaches its destination, it's morphed into a muon or tau neutrino. This shape-shifting isn't just a quirky trait. It suggests that neutrinos might treat matter and antimatter differently, violating CP symmetry in ways we're only beginning to understand. Here's where things get intriguing. If neutrinos oscillate differently than their antimatter counterparts, antineutrinos, that asymmetry could have tipped the scales in the early universe. Picture this: right after the Big Bang, neutrinos and antineutrinos were everywhere, constantly switching flavors. But if antineutrinos oscillated slightly less often, even by a fraction of a percent, that tiny difference could have left behind just enough extra matter to build everything we see today. It's like a cosmic coin flip that landed ever so slightly in matter's favor. To test this, physicists are running ambitious experiments like T2K in Japan and NRV in the United States. These projects fire beams of neutrinos and antineutrinos across hundreds of kilometers through the Earth itself, to detectors that catch them mid-oscillation. The goal: to spot any divergence in how neutrinos and antineutrinos behave. Early results hint at a possible asymmetry, but the data isn't conclusive yet. The stakes are high. If confirmed, neutrino CP violation could plug a major hole in our understanding of the matter-antimatter imbalance. What makes neutrinos such compelling suspects is their universality. They're not just bystanders, they were front-row witnesses to the universe's first moments. If their oscillations favored matter even slightly, that bias could have snowballed over billions of years into the overwhelming matter dominance we see now. It's a delicate process hidden in the faintest of particle interactions, but it might be the missing piece we've been searching for. Up next, we'll explore another bold idea: supersymmetry, and how it could amplify these subtle asymmetries into the universe we know. Now, let's step into the world of supersymmetry, a theory that stretches the imagination with its elegant but mysterious proposal. Supersymmetry, or SUSY for short, suggests that every particle we know, electrons, quarks, photons, has a hidden, heavier twin called a superpartner. Imagine a cosmic mirror where familiar particles have shadowy counterparts with quirky names like selectrons, squarks, and photinos. These superpartners aren't just for show. If they exist, they could solve some of physics' biggest puzzles, including the matter-antimatter imbalance. Here's how SUSY ties into our antimatter mystery. One of the Sakharov conditions requires CP violation, matter and antimatter behaving differently, and SUSY could supercharge this effect. In the early universe, superparticles and their regular counterparts might have decayed in slightly uneven ways, favoring matter over antimatter. Think of it like a pair of scales where one side is subtly weighted. Over time, even a tiny preference could tip the balance toward the matter-dominated cosmos we see today. SUSY doesn't just add new particles, it adds new ways for CP violation to happen, potentially explaining why matter won out. But there's a catch. Despite decades of searching, nobody has found a single superpartner. The Large Hadron Collider has hunted for them at higher energies than ever before, and so far the detectors have come up empty. This doesn't mean SUSY is wrong, but it does raise questions. Maybe superparticles are much heavier than we thought, hiding just beyond our current reach. Or perhaps they're so elusive that they interact with ordinary matter in ways we haven't figured out how to detect. Some theorists argue that SUSY might still be correct, but in a form we didn't expect. Instead of every particle having a perfect twin, maybe only some superpartners exist, or their properties differ from early predictions. Others suggest that SUSY's greatest value lies in the math itself. It elegantly solves problems like unifying forces or explaining dark matter, even if we never spot a superpartner directly. The absence of superparticles doesn't kill the theory, but it does make physicists rethink their assumptions. SUSY remains a compelling idea because it fills so many gaps in our understanding, from the hierarchy problem, why the Higgs boson is so light, to the puzzle of dark matter. If superparticles are out there, they could still be the missing link in our antimatter story. But for now, the search continues, and every null result pushes us to refine our theories. Up next, we'll dive into another bold idea, leptogenesis, where neutrinos take center stage again, but in a way that might surprise you. Now let's turn to another fascinating idea that could crack the antimatter mystery, leptogenesis. This theory puts neutrinos in the spotlight once more, but with a twist you might not see coming. Instead of focusing on the tiny neutrinos we know, it introduces hypothetical heavy neutrinos, often called right-handed neutrinos, and suggests their decay could have tipped the cosmic scales in favor of matter. Here's how it works. In the early universe, these heavy neutrinos would have been unstable, decaying into lighter particles. But here's the catch: they wouldn't have decayed symmetrically. Just like a slightly unbalanced coin toss, their decay would have produced a tiny bit more matter than antimatter. Over time, this small bias could have snowballed into the overwhelming matter dominance we observe today. This idea ties neatly into something called the seesaw mechanism, which helps explain why neutrinos are so incredibly light. The theory suggests that while most particles have masses in a familiar range, neutrinos could have ultra-heavy partners. The heavier these right-handed neutrinos are, the lighter the ordinary neutrinos we detect become, hence the name seesaw. It's a cosmic balancing act that not only explains neutrino masses, but also provides a perfect setup for leptogenesis to happen. Grand unified theories, or GUT, add another layer to this picture. These theories aim to merge three of nature's fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, into a single framework. In many JUTs, heavy neutrinos emerge naturally, and their decay fits perfectly into the leptogenesis story. If these theories are correct, the universe's matter-antimatter imbalance might be a direct consequence of forces unifying at unimaginably high energies shortly after the Big Bang. What's especially elegant about leptogenesis is how it connects small-scale particle physics to the grand structure of the cosmos. Unlike supersymmetry, which introduces a whole new family of particles, leptogenesis builds on neutrinos, particles we already know exist, while proposing just a few extra heavyweight players. It's a minimalist yet powerful explanation, and experiments studying neutrino oscillations like T2K and N of A are already hunting for hints of the CP violation that would make this scenario possible. Of course, leptogenesis isn't without its challenges. Those heavy neutrinos have never been detected, and their existence remains purely theoretical for now. But the same was once true of the Higgs boson until it wasn't. Future experiments like the Deep Underground Neutrino Experiment (DUNE) could provide crucial clues, especially if they spot evidence of neutrinos and antineutrinos behaving differently. So while leptogenesis might sound like a speculative idea, it's grounded in well-tested physics and offers a compelling path forward. It's a reminder that sometimes the answers to the universe's biggest mysteries lie in the smallest, most elusive particles. Up next, we'll shift gears and explore how antimatter isn't just a cosmic curiosity. It's already playing a role in cutting-edge technology right here on Earth. Now let's take a step back from the cosmos and see how antimatter is making waves right here on Earth. While it might sound like something from a futuristic novel, antimatter isn't just theoretical, it's already at work in some of today's most advanced technologies. One of the most well-known applications is in medical imaging, specifically positron emission tomography or PET scans. Here's how it works. Doctors inject a patient with a tracer, a harmless radioactive substance that emits positrons, the antimatter twins of electrons. When those positrons encounter electrons in the body, they annihilate each other, releasing bursts of energy in the form of gamma rays. Detectors pick up these signals, creating detailed 3D images of tissues and organs. It's a brilliant example of how antimatter helps us see inside the human body, diagnosing diseases like cancer long before symptoms appear. But medicine isn't the only field where antimatter shows promise. Imagine spacecraft zipping between planets or even stars, powered by the most efficient fuel imaginable. That's the dream behind antimatter propulsion. When matter and antimatter annihilate, they release energy with near-perfect efficiency, far surpassing chemical rockets or even nuclear propulsion. Just 1 gram of antimatter could deliver the same energy as tens of thousands of tons of conventional rocket fuel. Projects like NASA's early-stage concepts explore how tiny amounts of antimatter might one day propel probes to Mars in weeks instead of months. Then there's the ultimate sci-fi challenge, antimatter as an energy source. Theoretically, annihilating matter and antimatter could provide an unimaginably powerful energy supply, but here's the problem. Creating and storing antimatter is astronomically difficult and expensive. The world's most advanced facilities, like CERN, produce only vanishingly small amounts, measured in billionths of a gram. To make just 1 gram would take thousands of years at current rates, costing roughly $62 trillion. And storage, antimatter can't touch ordinary matter without exploding, so we rely on magnetic traps to suspend it in perfect isolation, a technology still in its infancy. That's why, for now, antimatter remains more of a scientific marvel than a practical tool. The challenges of production, containment, and cost make large-scale use a distant dream. But the same was once said of electricity, nuclear power, and even space travel. Every leap begins with small steps, and the experiments happening today could pave the way for breakthroughs we can barely envision. Next, we'll dive into one of those cutting-edge experiments, CERN Alpha-G project, which might finally answer a mind-bending question about antimatter's behavior under gravity. Now, let's shift our focus to one of the most intriguing questions in modern physics: does antimatter fall up or down? This might sound like a simple curiosity, but the answer could shake the very foundations of our understanding of gravity. Enter the Alpha-G experiment at CERN, where scientists are putting antimatter to the ultimate test. For decades, we've assumed that antimatter behaves just like matter under gravity, that it falls downward, not upward. After all, Einstein's theory of general relativity treats all mass equally, whether it's matter or antimatter. But what if that assumption is wrong? If antimatter defies expectations and falls upward, it would force us to rewrite the laws of physics. That's why the Alpha-G team is meticulously studying antihydrogen atoms, the simplest form of antimatter, to see how gravity interacts with them. Here's how the experiment works. Scientists trap antihydrogen in a magnetic bottle, suspending it in a near-perfect vacuum to prevent annihilation. Then they slowly weaken the magnetic field, allowing the antimatter to escape and interact with gravity. Ultra-sensitive detectors track whether these particles rise or fall. It's an incredibly delicate process. Antimatter is notoriously hard to work with, and even the slightest interference could skew the results. In 2023, the Alpha-G collaboration released their first major findings. After analyzing hundreds of antihydrogen atoms, they observed that antimatter does, in fact, fall downward, just like ordinary matter. At first glance, this might seem like a confirmation of the status quo, but dig deeper and the implications are profound. By ruling out the possibility of antimatter falling up, the experiment reinforces Einstein's equivalence principle, which states that gravity acts the same on all objects regardless of their composition. This consistency is crucial for our models of the universe, from black holes to the Big Bang. Yet, the story isn't over. The 2023 results still leave room for tiny deviations, hints that antimatter might interact with gravity slightly differently than matter. Future experiments with even greater precision could uncover these subtle differences, potentially revealing new physics beyond Einstein's framework. Some theories, like certain versions of supersymmetry, predict such anomalies. If detected, they could help explain why the universe is dominated by matter, solving the very mystery we've been exploring. So while Alpha-G hasn't overturned physics yet, it's a giant leap toward understanding antimatter's role in the cosmos. Every data point brings us closer to answering whether gravity treats matter and antimatter as perfect mirrors, or if there's a hidden asymmetry waiting to be discovered. Next, we'll explore another cosmic puzzle. Could antimatter be linked to the elusive dark matter that shapes our universe? The connections might surprise you. Now, let's venture into one of the most fascinating frontiers of cosmic mystery, the potential connection between antimatter and dark matter. At first glance, these two might seem unrelated, but digging deeper reveals threads that could tie them together in ways that rewrite our understanding of the universe. Dark matter, that invisible scaffolding holding galaxies together, makes up roughly 27% of the cosmos, yet we've never directly detected it. Antimatter, on the other hand, we can create and study in labs, but it's vanishingly rare in nature. So what if dark matter is secretly producing antimatter? This idea isn't science fiction. Some theories suggest that when certain types of dark matter particles decay or collide, they could spawn positrons, the antimatter counterparts of electrons. If true, this would explain why we've detected far more positrons in space than expected. Enter the Alpha Magnetic Spectrometer, or AMS-02, a detector mounted on the International Space Station. Since its launch in 2011, AMS-02 has been meticulously counting cosmic rays, including an unexpected excess of high-energy positrons. While some positrons naturally come from pulsars or other cosmic phenomena, the sheer number detected hints at something more exotic. Could dark matter be the source? It's a tantalizing possibility, but not the only one. Pulsars, the rapid spinning remnants of dead stars, also produce positrons, making it a cosmic detective game to pinpoint the true culprit. The plot thickens when we consider the energy spectrum of these positrons. Dark matter decays would likely produce a smooth, predictable distribution of positron energies, while pulsars might create a more irregular pattern. So far, AMS-02's data leans toward a smooth curve, fueling the dark matter hypothesis. But scientists remain cautious. Without a definitive smoking gun, like a sudden spike in positrons at a specific energy, the mystery endures. This isn't just academic curiosity. If dark matter does produce antimatter, it could help solve two puzzles at once. First, it would give us a new way to indirectly detect dark matter, something that's eluded physicists for decades. Second, it might shed light on why our universe has so little antimatter. If dark matter decays are spewing out positrons, could they have played a role in tipping the scales toward matter dominance in the early cosmos? Of course, alternative explanations exist. Some physicists argue that the positron excess could come from undiscovered astrophysical objects or even flaws in our models of cosmic ray propagation. The beauty of science lies in this uncertainty. Every answer leads to new questions. Upcoming experiments like the next generation of space-based detectors or more sensitive underground labs could finally crack the case. What's clear is that the dance between antimatter and dark matter is far from over. Whether they're connected or not, each clue brings us closer to understanding the invisible forces shaping our universe. Next, we'll zoom out to see how even the tiniest imbalance between matter and antimatter, just one extra particle in a billion, created everything we see around us. The numbers might surprise you. Now, let's put this cosmic puzzle into perspective by breaking down the numbers. Imagine the early universe as a perfectly balanced scale, with matter on one side and antimatter on the other. In theory, the Big Bang should have created equal amounts of both, leaving nothing behind after annihilation. Yet here we are in a universe brimming with galaxies, stars, and planets, all made of matter. So what tipped the scales? The answer lies in a staggeringly small imbalance, one so tiny it's almost absurd. For every billion antimatter particles produced in the early universe, there were 1,000,001 matter particles. That's a difference of just one extra matter particle in a billion. To put it another way, if you had $1 billion and spent exactly $1 billion, you'd expect to have nothing left. But in our universe's case, you'd somehow still have a single dollar remaining. This minuscule surplus is what built everything we see today. After all the annihilation settled down, that 1 in a billion excess of matter was all it took to seed the cosmos. But how could such a slight imbalance lead to the vast universe we inhabit? Think of it like a snowball rolling downhill. In the first fractions of a second after the Big Bang, particles and antiparticles were colliding and annihilating at an unimaginable rate. For every billion annihilations, one matter particle slipped through untouched. Over time, as the universe expanded and cooled, these survivors became the building blocks of atoms, then stars, then galaxies. What started as a 1 part in a billion difference eventually grew into the matter-dominated cosmos we know. This raises another question: why didn't the universe end up perfectly balanced? If matter and antimatter were truly symmetrical, there should have been zero excess matter left. That's where CP violation comes back into play. As we discussed earlier, certain particle interactions treat matter and antimatter slightly differently, creating a tiny bias in favor of matter. Over the unfathomable number of interactions in the early universe, this bias added up to that crucial 1 in a billion surplus. To grasp just how precise this imbalance had to be, consider this. If the matter-antimatter asymmetry had been even slightly larger, say, 1 extra matter particle in a million instead of a billion, the universe would have been far denser, with matter clumping together too quickly for galaxies to form. If it had been smaller, there might not have been enough matter left to create anything at all. Our existence hinges on this razor-thin edge of cosmic luck. So where does this leave us? That 1 in a billion imbalance wasn't just a random fluke. It was the result of fundamental physics, likely tied to the same CP violation we've detected in particle experiments. It's a reminder that the universe's grandest structures owe their existence to the tiniest of details. Next, we'll explore how quantum fluctuations during cosmic inflation might have amplified this asymmetry, setting the stage for the universe we call home. Now, let's take a step deeper into the quantum realm to uncover how the universe's tiny matter surplus might have gotten its start. Picture the earliest moments of the cosmos, a trillionth of a second after the Big Bang, when space itself was expanding faster than light, a period scientists call cosmic inflation. During this explosive growth spurt, the fabric of reality wasn't just stretching, it was fizzing with quantum fluctuations, tiny, random blips of energy popping in and out of existence. These fluctuations weren't just background noise, they were the cosmic dice rolls that may have tipped the scales toward matter. Here's how it works. In the quantum world, particles and antiparticles constantly emerge as fleeting pairs, borrowing energy from the vacuum before annihilating and returning it. Normally, these pairs cancel each other out perfectly, but during inflation, the universe's rapid expansion could have stretched these quantum ripples across vast distances, freezing them into place before annihilation could occur. Now add CP violation to the mix. If these particle-antiparticle pairs didn't behave symmetrically, if matter and antimatter decayed at slightly different rates, as experiments suggest, then quantum fluctuations could have favored matter by the slimmest of margins. Imagine flipping a loaded coin trillions of times. Even if it's only slightly weighted over enough flips, you'd end up with a noticeable imbalance. In the seething quantum foam of the early universe, that's exactly what might have happened. This idea gains even more traction when you consider how inflation magnified these effects. Think of blowing up a balloon with microscopic dots drawn on it. As the balloon expands, tiny imperfections get stretched into large-scale patterns. Similarly, infinitesimal quantum biases, amplified by inflation, could have grown into the vast matter-dominated regions we see today. The galaxies in our night sky might owe their existence to subatomic imbalances stretched across cosmic scales. But here's the twist: quantum fluctuations alone wouldn't have been enough. Without CP violation, any matter excess from fluctuations would have been wiped out by subsequent annihilations. The universe needed both ingredients: random quantum noise and a fundamental asymmetry in the laws of physics, to cook up the matter surplus we observe. It's like baking a cake where the recipe calls for both yeast and sugar. One makes the dough rise while the other gives it flavor. To grasp the scale of this process, consider that the entire observable universe, all 2 trillion galaxies, might trace back to quantum ripples in a region smaller than a proton. That's how powerful inflation was at sculpting our cosmos. And if CP violation nudged those ripples even slightly toward matter, it would explain why we're here at all. This brings us to a profound realization. The universe's grand structure, from galaxy clusters to the atoms in our bodies, may hinge on quantum randomness frozen in during its first moments. Yet randomness alone doesn't explain the precise 1 in a billion imbalance. That required physics itself to play favorites, however subtly. Next, we'll venture into even wilder territory. Could pockets of antimatter have survived inflation, lurking in the cosmos as stars or even entire galaxies? The answer might surprise you. Now, let's turn our gaze to one of the most tantalizing what-ifs in cosmology: antimatter stars. Imagine a star that looks just like any other, blazing in the void but with a terrifying twist. Its core isn't fusing hydrogen like our sun, it's annihilating antimatter. The idea isn't as far-fetched as it sounds. Theoretically, if some regions of the early universe escaped the matter-antimatter annihilation spree, pockets of antimatter could have collapsed into stars or even whole galaxies. Picture a mirror version of our Milky Way, where every atom is flipped: protons are negative, electrons positive. But here's the catch: if such objects existed, we'd know. When antimatter meets ordinary matter, it doesn't just vanish quietly. The annihilation fireworks unleash gamma rays with a very specific energy signature: 2 photons at 511,000 electron volts each, the telltale fingerprint of electron-positron annihilation. Astronomers have scoured the skies for decades hunting these gamma ray beacons. The results: a resounding silence. the Milky Way's diffuse gamma-ray background shows no concentrated bursts from antimatter stars. Even more telling, when neighboring galaxies collide, their gas clouds mingle. If any were made of antimatter, we'd see massive annihilation fronts like cosmic demolition derbies lighting up the night. But all we observe are ordinary stellar collisions. That hasn't stopped theorists from proposing exotic loopholes. Some suggest antimatter stars might lurk in cosmic voids, so isolated they rarely interact with matter. Others speculate about quark stars with surfaces that convert matter into antimatter, masking their true nature. The most radical idea: primordial antimatter black holes left over from the Big Bang, their signatures hidden behind event horizons. Yet the simplest explanation remains the likeliest. Inflation likely smoothed out any antimatter patches before they could grow large. Quantum fluctuations and CP violation didn't just favor matter. They may have erased antimatter's cosmic real estate entirely. Still, the search continues. Projects like the Alpha Magnetic Spectrometer on the International Space Station keep sifting cosmic rays for anti-helium nuclei, smoking guns of distant antimatter factories. For now, antimatter stars remain in the realm of captivating speculation, but their hypothetical existence teaches us something profound. The absence of evidence isn't just a null result. It's another clue in the mystery of why our universe is made of stuff rather than its shadow. Next, we'll see how today's scientists are pushing the boundaries of this enigma with experiments that could rewrite the rules of reality itself. Shifting our focus from cosmic mysteries to cutting-edge laboratories, the hunt for antimatter's secrets is entering its most exciting phase yet. Scientists worldwide are gearing up for experiments that could finally crack the code of why matter dominates our universe. At the forefront is CERN, where the Large Hadron Collider is set to receive a major upgrade by 2029. Dubbed the High Luminosity LHC, this supercharged version will smash particles with unprecedented precision, allowing researchers to study rare antimatter events with a clarity never before possible. Imagine catching a glimpse of CP violation in exotic particles like beauty quarks, something that could tip the scales in explaining matter's cosmic victory. Meanwhile, across the Atlantic, the Deep Underground Neutrino Experiment, or DUNE, is preparing to unravel another piece of the puzzle. Nestled over a mile beneath South Dakota, this massive detector will track neutrinos beamed from Fermilab in Illinois. Why neutrinos? These ghostly particles might hold the key to extreme CP violation. If they oscillate differently from their antimatter counterparts, it could explain how the early universe favored matter. DUNE ultra-sensitive sensors could spot these tiny asymmetries, potentially rewriting our understanding of particle physics. But the search isn't confined to Earth. Space-based detectors like the Alpha Magnetic Spectrometer, mounted on the International Space Station, continue to scan cosmic rays for traces of anti-helium or even heavier antinuclei. Finding just a few of these could hint at undiscovered antimatter domains in distant galaxies. And then there's the proposed anti-proton decelerator upgrade at CERN, aiming to produce and trap enough cold antihydrogen to test whether it falls upward in gravity, a discovery that would upend Einstein's equivalence principle. What breakthroughs might the next decade bring? Experts speculate we could confirm leptogenesis, proving that heavy neutrinos decayed unevenly after the Big Bang. Or we might find evidence of supersymmetry, revealing particles that amplify CP violation. Some even dream of synthesizing stable antimatter compounds, though that remains a distant frontier. One thing's certain, each experiment brings us closer to solving one of physics' greatest riddles. The answers won't just satisfy curiosity, they could redefine the fundamental laws governing reality itself. As these projects unfold, they remind us that science's greatest revelations often come from asking simple questions. Why are we here? Why is there something rather than nothing? The tools to find those answers are now within our grasp, waiting to uncover the universe's best-kept secret. Now let's step away from the lab for a moment and dive into something a bit more playful: how antimatter fuels our favorite stories. Hollywood loves a good sci-fi plot, and antimatter often gets cast as the ultimate doomsday device or cosmic superfuel. Take Angels and Demons, where a stolen vial of antimatter threatens to level the Vatican. The film nails the raw power of matter-antimatter annihilation, but real-world antimatter is far too scarce to weaponize. In reality, CERN produces mere billionths of a gram per year, and storing it requires ultra-complex magnetic traps. That cinematic heist, it'd cost trillions to pull off. Then there's Half-Life, where antimatter powers the gravity gun. While the game's physics-defying gadgets are pure fantasy, the idea isn't entirely off base. NASA has toyed with antimatter propulsion concepts where tiny amounts could fuel interstellar missions. But here's the catch: generating even a milligram would take decades and a power plant's worth of energy. Games and movies skip the logistics, but that's what makes them fun. Pop culture also loves painting antimatter as some shadowy, exotic force like Star Trek's warp cores humming with antimatter containment. In truth, antimatter isn't lurking in dark corners of the universe. When it forms naturally, say near black holes, it's instantly obliterated by surrounding matter. Those dramatic gamma-ray bursts, they're just antimatter's fleeting goodbye. The biggest myth, that antimatter is common. Films like the Da Vinci Code spin tales of ancient antimatter vaults, but in our universe it's vanishingly rare. Even the famed Fermi bubbles, giant cosmic structures near our galaxy's center, emit traces of antimatter, but at levels dwarfed by ordinary matter. So why the hype? Antimatter taps into our love for the extreme. It's the ultimate what-if with real science roots, and while Hollywood exaggerates, it sparks curiosity. After all, who wouldn't wonder about a substance that could power cities or vanish mountains? Just remember, the real magic isn't in doom scenarios. It's in the quiet labs where scientists unravel antimatter's true secrets, one atom at a time. Now let's pivot to a serious question lurking behind all the sci-fi excitement. Could antimatter actually become a real-world threat? The idea of weaponizing antimatter isn't just Hollywood fiction. It's been studied by defense agencies, but the challenges are staggering. First, there's the production problem. Creating even a single gram of antimatter would require the energy output of several nuclear power plants running continuously for decades. At current production rates, CERN's entire annual output would barely fill a grain of sand. And then there's the price tag, an estimated $62.5 trillion per gram, making it the most expensive substance on Earth by a cosmic margin. But let's say money and energy weren't obstacles. Storage is the next nightmare. Antimatter can't touch ordinary containers. It would instantly annihilate on contact. Instead, scientists use ultra-powerful magnetic traps called penning traps, which suspend antimatter in a vacuum using electromagnetic fields. These setups are fragile, though. A single power fluctuation or mechanical failure could release the antimatter, triggering a catastrophic explosion. Even the most advanced labs lose tiny amounts daily, hardly reassuring for anyone picturing a stockpile. Then there's the physics of destruction. While antimatter packs unparalleled energy density, a gram could match a 20-kiloton nuke. Delivering it as a weapon is wildly impractical. Unlike uranium or plutonium, you can't just assemble a critical mass. Antimatter must be precisely contained until detonation, requiring a delivery system more complex than the bomb itself. Plus, the annihilation process releases intense gamma rays, which are deadly but don't produce the lingering fallout of nuclear weapons. Ironically, the very efficiency of antimatter annihilation makes it a blunt instrument compared to the radioactive aftermath of fission bombs. Safety protocols at facilities like CERN are designed to prevent even microscopic leaks. Multiple fail-safes, redundant power supplies, and rigorous monitoring ensure that stored antimatter poses no public risk. And here's the ultimate comfort. The scale needed for weaponization is so far beyond current technology that it's firmly in the realm of speculation. Even if someone diverted every antimatter research facility on Earth, they'd barely collect enough for a firecracker. The real ethical dilemma isn't about doomsday devices, it's about resource allocation. With antimatter research costing billions, some argue the funds could tackle more immediate problems. Yet the potential payoffs: revolutionary energy solutions, medical breakthroughs like targeted cancer treatments, keep the science moving forward. So while antimatter won't be fueling supervillain plots anytime soon, its study continues to walk a delicate line between ambition and responsibility. Now let's take a step into the truly mind-bending what if the universe's matter-antimatter imbalance isn't just a physics puzzle but a doorway to existential questions. Enter the Boltzmann brain paradox, a thought experiment that ties antimatter to one of philosophy's biggest head-scratchers. Imagine this: if matter can randomly assemble over infinite time, shouldn't self-aware entities like human brains occasionally pop into existence purely by chance? That's the crux of the paradox, named after physicist Ludwig Boltzmann. But here's where antimatter twists the knife. If matter and antimatter were perfectly symmetrical at the Big Bang, why wouldn't random fluctuations also create antimatter brains? Yet we don't see them, not a single self-aware positron-powered consciousness floating in space. This isn't just sci-fi speculation. The absence of antimatter Boltzmann brains highlights how unrandom our universe really is. The fact that we're made of matter and that matter dominates suggests something fundamentally skewed the cosmic dice. CP violation might explain part of it, but the deeper implication is staggering. Our universe's laws seem fine-tuned to favor matter-based life. The slightest tweak to physics constants like the strength of gravity or the mass of electrons would have left the cosmos barren. Some theorists argue that if antimatter brains did form, they'd annihilate instantly in our matter-rich universe, leaving no trace. Others counter that even fleeting existence would leave detectable quantum ripples, yet we've found none. This silence isn't just a curiosity. It's evidence that antimatter doesn't behave like a mirror of matter in all ways. The paradox forces us to confront how peculiarly hospitable our universe is. For life to exist, matter had to win, but not by too much. Total annihilation would have left nothing, while total matter dominance allowed galaxies and biochemistry to emerge. It's a Goldilocks imbalance, and antimatter's near absence is the shadow that makes our cosmic story possible. So next time you hear about antimatter experiments, remember, they're not just hunting for exotic particles. They're testing whether we live in a universe that had to turn out this way, or if, against all odds, we're the lucky winners of a trillion-sided dice roll. And that's a mystery even Boltzmann couldn't solve. Now, let's venture into one of the most tantalizing what-ifs in modern physics. What if antimatter isn't just a rare counterpart to matter, but a window into an entirely separate universe? Picture this: a mirror cosmos where antimatter dominates, stars are made of positrons, and time might even flow backward. This isn't just wild speculation. It's a fringe theory grounded in a deep principle called CPT symmetry. At its core, CPT symmetry is like the universe's ultimate balancing act. It stands for charge, parity, and time, three fundamental symmetries that, when combined, should make the laws of physics perfectly reversible. Here's the twist: while matter and antimatter individually violate some of these symmetries, like CP violation we discussed earlier, physicists believe the full CPT combo must always hold true. If it doesn't, Einstein's relativity crumbles. So if you flip a particle's charge, mirror its position, and reverse time, it should behave exactly like its antimatter twin. This is where things get surreal. Some theorists propose that antimatter could literally be ordinary matter moving backward in time. Imagine an electron rewinding the cosmic clock. It'd look just like a positron moving forward. This idea birthed the mirror universe hypothesis, a parallel reality where antimatter isn't just rare but the default, with its own history and perhaps even life. If true, the Big Bang might have created two universes, one made of matter, ours, and one of antimatter, linked by CPT symmetry like cosmic twins. But why haven't we detected this mirror realm? One explanation is that the two universes are causally disconnected, forever separated by the Big Bang's aftermath. Another wild idea suggests that antimatter's reverse time behavior means our experiments can't easily spot it. For instance, if a mirror star exploded, the light might reach us as an inexplicable gamma-ray burst, or not at all if time flows oppositely there. Critics argue this leans too heavily into metaphysics, but experiments aren't ruling it out. CERN Alpha collaboration is testing whether antimatter falls up in gravity, which could hint at exotic physics beyond CPT. Meanwhile, cosmic ray detectors scour the skies for anomalies that might betray a mirror universe's presence. Whether or not mirror universes exist, the theory underscores a profound truth. Antimatter isn't just a missing puzzle piece in our cosmos. It might be the key to understanding realities beyond our own, where time, space, and existence itself play by different rules. And that's a frontier worth exploring. Now, let's stretch our imagination even further. What if our matter-dominated universe isn't the only one out there? Picture an endless cosmic tapestry where countless universes bubble into existence, each with its own unique rules. Some might be flooded with antimatter, others with dark matter, or substances we haven't even dreamed of. This isn't science fiction, it's the multiverse hypothesis, and antimatter could play a starring role in this grand cosmic drama. The idea of the multiverse isn't just wild speculation. It emerges naturally from theories like cosmic inflation, which suggests our universe is one of many bubbles that inflated rapidly after the Big Bang. In this scenario, the laws of physics and even the balance between matter and antimatter might vary from one universe to another. Some bubbles could have ended up with perfect symmetry, annihilating into pure energy. Others, like ours, might have tipped slightly in favor of matter. And then there's the tantalizing possibility of bubbles where antimatter won the cosmic coin toss, creating realms where positrons orbit antiprotons in anti-atoms and anti-stars light up anti-galaxies. Why haven't we stumbled upon these antimatter universes? The answer lies in the very nature of the multiverse. If other universes exist beyond our cosmic horizon, their light hasn't had time to reach us since the Big Bang. They're literally beyond our observational limits. Even if an antimatter galaxy were just next door, the space between us is expanding faster than light can traverse it, sealing it off forever. Some theories suggest that if antimatter universes are out there, the only hint might come from rare quantum fluctuations or anomalies in the cosmic microwave background, echoes of collisions with other bubbles in the multiverse's frothy landscape. Critics argue that the multiverse is untestable, but physicists aren't giving up. Some look for subtle imprints in the cosmic microwave background, like cold spots or unusual patterns that could betray a long-ago brush with another universe. Others hunt for evidence in the behavior of antimatter itself, like the Alpha-G experiment, which tests whether antimatter falls differently in gravity. If it does, it might hint at exotic physics that could support the multiverse idea. Whether or not we ever find proof, the multiverse hypothesis reshapes how we think about antimatter's scarcity. Instead of a cosmic accident, our matter-dominated universe might be just one outcome in a vast ensemble of possibilities. And that raises an even wilder question. In an infinite multiverse, could there be a version of you made entirely of antimatter, pondering why their universe has so little ordinary matter? The answer, for now, remains hidden in the cosmic deep. But here's the takeaway. Antimatter isn't just a missing piece of our universe's puzzle. It might be the thread connecting us to realities beyond our wildest imagination, where the rules are different, the stars are made of opposites, and the cosmos is far stranger than we ever guessed. And that's a mystery worth chasing. Now, let's tackle one of the biggest mix-ups in physics, the confusion between antimatter and dark matter. At first glance, they might sound like two sides of the same cosmic coin, but they're as different as apples and asteroids. Antimatter, as we've seen, is the mirror image of ordinary matter, with particles like positrons and antiprotons that annihilate on contact with their counterparts. Dark matter, on the other hand, is something entirely else, invisible, mysterious, and detectable only by its gravitational pull on galaxies. Think of antimatter as the rebel twin of matter, while dark matter is the cosmic ghost we're still trying to unmask. Another common myth is that antimatter exists only in science labs or theoretical equations. The truth, it's all around us, just in tiny amounts. For example, every banana emits about 1 positron, a type of antimatter, per hour due to natural radioactive decay. Even thunderstorms create bursts of antimatter in the form of positrons, detected by satellites like NASA's Fermi telescope. And let's not forget medical technology. CT scans used in hospitals worldwide rely on positrons to map everything from brain activity to tumors. So no, antimatter isn't some far-off fantasy. It's part of our daily lives, just on a scale too small to notice without the right tools. Then there's the idea that antimatter is too unstable to study. Sure, it vanishes in a flash when it meets matter, but scientists have gotten incredibly clever at trapping it. At CERN, experiments like ALPHA use magnetic fields to hold antihydrogen atoms in place for minutes at a time, long enough to probe their properties with lasers. These aren't just party tricks, they're critical tests of whether antimatter follows the same rules as matter. If it doesn't, we might finally crack why our universe favors one over the other. Some folks even think antimatter could power cities or warp drives tomorrow. The reality, making just 1 gram of it would cost tens of trillions of dollars and take centuries at current production rates. But that doesn't mean it's useless. Beyond medicine, antimatter helps us test fundamental physics, like whether gravity pulls on it the same way, a question the AlphaG experiment is tackling right now. The bottom line, antimatter isn't dark matter, it's not just theory, and it's not magic fuel. It's a real, detectable piece of the universe's puzzle, one that's helping us ask better questions about why everything exists. And that's a story far more exciting than any myth. Now, let's take a step back and imagine a universe where antimatter called the shots. Picture this: instead of the galaxies and stars we know, everything is made of antimatter, antiplanets, antistars, even anti-you. At first glance, it might seem like nothing would change. After all, antimatter behaves just like matter, right? Well, not so fast. The moment any ordinary matter drifted into this anti-universe, say, a stray hydrogen atom, it would vanish in a burst of energy upon contact. No stars could form near antistars, no planets could orbit them without being obliterated. The cosmic landscape would be a minefield of annihilation, leaving little room for the stable structures that make life possible. This raises a haunting question: could life even exist in such a place? The answer is probably no, and here's why. Life as we know it depends on complexity, molecules building cells, cells forming organisms. But in an antimatter-dominated cosmos, the constant threat of annihilation would shred any delicate chemical bonds before they could assemble into something meaningful. Forget DNA or proteins, even simple molecules would struggle to survive. It's like trying to build a sandcastle in a hurricane. The universe would be stuck in a permanent state of destruction, with no chance for the slow, patient dance of chemistry that led to us. Now contrast that with our own matter-rich universe. Here, the scarcity of antimatter is a cosmic blessing. Stars burn steadily for billions of years, planets orbit undisturbed, and chemistry unfolds uninterrupted. That tiny imbalance after the Big Bang, the one that left us with just a fraction more matter, was the ultimate lucky break. Without it, the universe might have been a fleeting firework of particle collisions over almost before it began. Instead, we got longevity, stability, and the chance for life to emerge. But let's push this further. What if antimatter wasn't just dominant but exclusive? A universe with only antimatter and zero ordinary matter might avoid annihilation altogether, behaving just like ours but with a sign flip. The real puzzle isn't why antimatter lost, it's why matter won. Because either scenario could have been equally likely, yet here we are in a universe made of matter, puzzling over its absence. This isn't just speculation. It's a reminder of how fine-tuned our existence really is. The fact that we're here to ask these questions hinges on an asymmetry so slight, it's like winning the cosmic lottery. And that's what makes antimatter more than a physics curiosity. It's a clue to why the universe looks the way it does and why we're around to notice. So next time you gaze at the stars, remember, their light reaches us only because matter got the upper hand, and that's a victory worth celebrating. Here's the next part of the script, seamlessly continuing from the previous section while introducing the conclusion with a fresh transition. Now, stepping back from the cosmic what-ifs, let's piece together what we do know. The mystery of matter's dominance boils down to a few groundbreaking ideas, each a thread in physics' grand tapestry. First, CP violation, that subtle crack in the mirror between matter and antimatter, where particles don't quite behave as perfect opposites. Remember those kaons from the 1960s? Their lopsided decays were the first clue that the universe might have a favorite. Then there's leptogenesis, the elegant twist where heavy neutrinos could have tipped the scales, decaying just a bit more into matter than antimatter. And let's not forget Sakharov's recipe, those three cosmic conditions needed to cook up our matter-rich reality. But theories alone aren't enough. Science thrives on proof, and that's where experiments like alpha and base at CERN come in. Trapping antihydrogen to study its gravity-defying quirks, or smashing particles in the LHC to hunt for CP violations' fingerprints, these are the trenches where answers are forged. Even neutrino detectors like T2K, watching these ghostly particles flip flavors, are chasing the same cosmic imbalance. Yet for all our ingenuity, the puzzle isn't solved. Every experiment leaves room for more questions, more tantalizing maybes. So where does that leave us at the edge of discovery with a universe that's still whispering its secrets? Maybe the answer lies in supersymmetry's unseen particles, or in quantum ripples during inflation. Or perhaps it's something no theorist has yet dreamed up. One thing's certain, the solution won't just fill a textbook, it'll rewrite the rules of reality itself. That's the thrill of this mystery. It's not just about antimatter, it's about understanding why anything exists at all. So stay curious, keep looking up, and tell me in the comments which theory grabs you. CP violations, tiny cracks, neutrinos playing cosmic favorites. Or something wilder. The conversation doesn't end here. If you're as hooked as I am, hit that subscribe button to dive deeper into the universe's biggest puzzles. Until next time, keep wondering. After all, the next eureka moment could be yours.